Dear students, Assalamu alaikum. Today I will talk about electric potential part 1. But before going to the concept of electric potential, I will give an overview to the concepts of potential energy and conservative forces. So first talk about conservative force. We know that gravitational force and electric force are conservative forces. And why they are called conservative forces? Because the burden by these forces doesn't depend upon the path. Second, the burden by these forces around a closed path is zero. To describe this, we consider a curved path A, where a charge is moved from point 1 to 2 by an electric force F. dW is the burden by the electric force when a charge is moved by this force through a small distance ds. Note that ds has a direction along tangent to every point along path A, and the total work done along path A can be simply written as integrating this equation, where the integral sign is called a path integral, which indicates integration over path A from point 1 to 2. Now, in this figure, the initial position and the final position 1 and 2, they are same, but the paths are different. One is path A and the other is path B. So since the force is a conservative force, we can say that the work done along path A is equal to the work done along path B, as we can see here. Next, we consider a closed path which starts from point 1 to 2 along path A, and then from point 2 to 1 along path C. The total work done for this closed path can be written as work done along path A plus work done along path C, or we can write it that work done along path A minus work done along path B, because we can see that the work done path along path C is simply the negative of the work done along path B. And from here we know that work done along path A is equal to work done along path B. So the total work done around a closed path is equal to 0. Now we come to the concept of potential energy. As we observed that the work done by conservative force is path independent, means that if the initial position and the final position are same, then the work done does not depend upon the path. The work done will always be constant whatever path you follow. We also know from the introductory course of mechanics that the potential energy is always equal to the negative of the work done. So using that concept, we can define potential energy, that is du, which is potential energy, is equal to the minus w. W is the work done, that is integral f dot ds. And if the particle is moving from point 1 to point 2 or position 1 to 2, then we can write this relation du is equal to u2 minus u1 is equal to minus integral f dot ds. Here u1 is the potential energy at position 1 and u2 is the potential energy at position 2. To describe it further, consider an example. Here we have two charges q1 and q2. q2 is at a distance r1 from q1. Suppose q2 is moved from this position to this one, where it is at a distance r2 from q1. So using this definition of potential energy, we can write u2 minus u1 is equal to minus integral f dot dr. From the figure we can see that f and dr are parallel, so f dot dr becomes f times dr. F is the electric force, and using the magnitude of the force from Coulomb's law and inserting this relation for F here, this relation becomes S. and after simplifying this integral dr by r square, which is minus 1 over r plus c, so inserting this here we get this one, which after simplification the final equation can be written as. From this relation we note few points. Number one, if Q2 is moved from Q1, then in that case R2 becomes greater than R1, and we will have delta U less than 0, because this term 1 over R2 becomes minimum and 1 over this term becomes greater. So overall the right hand side term becomes negative. So we get delta U less than 0 and delta W greater than 0, and in this case the work is done by the electric repulsive force. But if Q1 and Q2 are of different sign, then delta U will be greater than 0 and delta W will be less than 0, and in this case the work is done by the electric attractive force. The second point which we note from that relation is that if Q2 moves towards Q1, then R2 becomes less than R1, and we will have delta U greater than 0 and delta W less than 0. But this will be if Q1 and Q2 are of the same size. So why delta U is greater than 0? The reason is that in this case, when R2 is less than R1, the right hand side term of the last equation becomes positive, which was negative in the first case. So therefore delta U will be greater than 0 and delta W will be less than 0. But if Q1 and Q2 are of different size, then delta U will be less than 0 and delta W will be greater than 0. The third point is that it is the difference in potential energy which is important, because whenever we measure potential energy, we always measure the difference in potential energy. And usually in potential energy calculation we set a reference point which is usually at infinity, and where the potential energy is 0. So in our case, if we set the second position of Q2 when it was at a distance R2, so if we set R2 to infinity and R1 to R and use inserting these in the last equations, and after simplification we will get this potential energy relation. So this is the potential energy expression for two charges Q1 and Q2 when they are separated by a distance R. So if Q1 and Q2 are of the same size, then the potential energy will be greater than 0 for all values of R, and if Q1 and Q2 are of opposite size, then potential energy will be less than 0 for all values of R. Next we come to the concept of electric potential V, which is potential energy U per unit charge Q. From the relation it is clear that electric potential V is a scalar, not a vector, and it has a unit joule per coulomb, which is often called volt. It is to be remembered that electric potential V does not depend upon the magnitude of charge Q. This is the characteristic of the electric field, where U, which is electric potential energy, depends upon the charge magnitude Q. In order to understand it, suppose we have a particle of charge Q in an electric field, and suppose it has a value of electric potential energy U at that point. Now, if we double the charge, if we replace that charge with that particle with another particle which has double the magnitude of charge, like it becomes 2Q, then its potential energy U will also be doubled. It will also be 2 times U. But the electric potential V, which is potential energy per unit charge, will remain the same. So electric potential V is independent of the charge magnitude Q, and electric potential energy U depends upon the charge magnitude. Potential difference delta V between 2 points I and F in an electric field is always equal to the change in potential energy per unit charge between the 2 points. We know that the change in potential energy is always equal to the negative of the work done. So using this relation here, we can write the potential difference relation as the negative of the work done per unit charge. So the potential difference between 2 points I and F is the negative of the work done to move a charge q from one point to another. If we set a reference point at infinity where potential energy is 0, so it is obvious that electric potential will also be 0 there. So using these values of Ui and Vi here, we define electric potential at a point in an electric field as the negative of the work done per unit charge, where W is the work done by the electric field to move a charge from infinity to a point in an electric field. Work done by an applied force. Suppose we want to move a charge from one point to another by applying a force to it. During the move, our applied force does work on the particle, and W is the work done by the electric field. So using the concept of work kinetic energy theorem, the total work done will be equal to the change in kinetic energy. But if the charge is stationary before and after the move, then delta K will become 0, and we are left with the work done by the applied force will be equal to the negative of the work done by the electric field. We know that delta U, which is the change in potential energy, is always equal to the negative of the work done. So from this we can write that delta U is equal to the work done by the applied force. And using this relation here, we can see that the work done by the applied force is equal to Q times delta V. It is also to be noted that work done by the applied force can be positive, negative, or 0, depends upon the signs and magnitudes of Q and delta V. Similarly, delta V can be positive, negative, or 0, depending upon the sign and magnitude of Q. And similarly, the electric potential V can also be negative, positive, or 0, depends upon the signs and magnitude of Q and W. The next is equipotential surface, means surfaces of the same potential. Since they are surfaces of the same potential, therefore the potential difference between any 2 points delta V is 0 per an equipotential surface. We will see later in the next section that potential due to a point charge V is equal to 1 over 4 pi epsilon naught Q over R. An equipotential surface may be a circle or spherical surface. So for a circle, R is always fixed or constant. So V is constant for an equipotential surface. As we can see here in the electric field pattern of a point charge Q, where electric field lines are radially outward lines, and 3 various concentric equipotential surfaces have shown, and for these surfaces we can see that V1 is greater than V2, V2 is greater than V3. The reason is that as we move away from the point charge Q, R increases, and since V is inversely proportional to R, so when R increases, V decreases. So therefore the outermost equipotential surface is a least equipotential surface as compared to the other 2 surfaces. You should also note that on an equipotential surface, a charge can move freely from one point to another without any work done. However, work is need to be done when we move a charge from one surface to another surface. Second, the electric field lines must be perpendicular to the equipotential surface. As we can see here that the tangential component dl, they are always perpendicular to the electric field, means E dot dl is 0, or in other words we say that delta V is 0. So therefore the electric field line must be perpendicular to the equipotential surface. Here we will see that how electric field E and electric potential V are related with each other. So we use two approaches. Number one, to get V from E, means that if we know the electric field E, how we will determine electric potential V from that. For this we consider a non-uniform electric field E, where a test charge Q naught has been moved from point I to point F by an electrostatic force Q naught times E. This electrostatic force Q naught times E acts on a test charge Q naught during the displacement ds. So if we recall the definition of the potential difference delta V, which is equal to change in potential energy per unit charge or negative of the work done per unit charge. So we can write this potential difference relation as V2 minus V1, where V2 is the potential at point F and V1 is the potential at point I, and this is the work done. Here F is the electrostatic force, which we can see here that it is equal to Q naught times E. So inserting this Q naught times E for F here, Q naught will cancel and we are left with E dot ds. So this is the potential difference between the two points 1 and 2 are points I and F in an electric field. Per convention, if we set point 1 at infinity, where the electric potential is 0, then the potential at point 2, or in other words the potential at point P, at which we want to determine the potential, that will be equal to the negative of the line integral of E dot ds. So from this relation, if we know the electric field E, we can determine V at that point P. The second approach is to get E from V, means that if we know the electric potential V, how we will determine E from that. For this we consider two surfaces. One surface is at a potential V and the other surface is of a potential V plus delta V. So they are two surfaces of different potential, means there is a potential difference between the two surfaces. So if we want to move a test charge Q naught from this surface to this surface, work is need to be done. So since there is a potential difference, so using the definition of potential difference, we can write the change in potential energy equal to Q naught times delta V, which is equal to the negative of the work done. And the work done in this case can be written as Q naught times E dot delta S. This is the electrostatic force. So since this is the electric field and ES is its component, so here it becomes Q naught ES delta S, because ES is the component of E along the direction of delta S. So equating these two relations, we get Q naught times delta V is equal to minus Q naught ES delta S, from which we get ES is equal to minus delta V by delta S. And for small displacement delta S, we can write this relation ES is equal to minus dV by ds. So ES is the component of the electric field along delta S. So the component of the electric field along any direction is equal to the negative of the derivative of the potential along that direction. Generalizing this equation for the x, y and z component, so we can write Ex is equal to minus partial v over partial x. For y, we can write it minus partial v over partial y. For Ez, we can write minus partial v over partial z. So using these relations, if we know the potential V, we can determine the electric field.